We're going to be doing some 8.5 today. 8.5, getting away from trig for a little bit. Well, sort of. It may show up a little bit still. But we're going to be doing partial fractions. So I hope that you've seen partial fractions in at least one of your courses in the past, whether it was Calc 1 or back in your algebra classes. So I'm going to do just a quick little review of partial fractions. So the way it works, it doesn't really matter what the numerator is. It could be anything. It's all about the denominator. If your denominator, let's say, had these linear terms in it, so maybe x minus 1 and x plus 2, both of these are to the 1 power, partial fraction decomposition is that we want to take this combined fraction and split it up. To do that, each one of your linear factors is going to get its own fraction. So we're going to have a fraction for x minus 1, and then separately we'll have a fraction for x plus 2. Because these are linear terms in the bottom, they're just going to get constants up top, so constant a and constant b. All right, from here, we would have to figure out what the a and the b is. That depends on what the numerator is, and I'll show you how to do that once we get into some examples. Other types of partial fraction decomposition is that sometimes you may have a power on one of your factors. So let's say you have x minus 1 all squared and then x plus 2 in the denominator. Anytime you have a power on one of your factors, you have to include a fraction with that power and then every single power all the way down to 1. So not only are we going to have an x minus 1 squared, but we're also going to have an x minus 1, and then don't forget that x plus 2, that's going to have 1 as well. It doesn't really matter what order you put the fractions, by the way. You can go in any order. So again, if you have a power on one of your linear terms, you have to include a fraction with that power and then a fraction for every single power all the way down to 1. So if this was cubed, you'd have a cubed, a squared, and then a linear one. The only other thing that you'll see is you may see quadratic factors. So let's say you had something like this, x squared plus 5. X squared plus 5 is an irreducible quadratic factor, and then we have this linear x minus 1. So that quadratic is going to get its own fraction, and of course the linear term gets its own fraction. But whenever you have a quadratic factor, you have to have a linear numerator. So it's not just a constant up top, it's going to be ax plus b, a linear polynomial here. This is just going to get a constant though. Okay, so that's my really quick crash course on partial fraction decomposition. Of course, we're going to do a bunch as we look at the examples from the book here. So let's just start off with this one. We're going to do the integral of 6x plus 7 all divided by x plus 2 all squared dx. Okay, so as it stands, right, we do have some techniques already that we saw from section 1 and onward, but none of those techniques is going to help for this question. You could try splitting up this fraction into two separate fractions, but it's just not really going to work out. So one technique that we can do is, as long as your denominator is somewhat factored, you can try partial fraction decomposition. So I'm going to go over to scratch paper. And let's take that 6x plus 7 all over x plus 2 all squared. And let's do the partial fraction decomposition. Because we have a linear term that is squared, we're going to have a fraction with that squared term with just a constant up top, and a fraction with that linear term to the 1 with a constant up top. All right, we need to figure out the a and the b. So the technique for doing that is we're going to multiply everything by the common denominator. The common denominator is this x plus 2 all squared. When I multiply it on the left-hand side, it cancels out, and we just get that numerator. Multiplying it on the right-hand side onto this first fraction, it cancels. Onto the second fraction, one of the x plus 2's cancel. The other one's going to be multiplied onto the b. All right, so at this point, there's a couple different ways to find the a and the b, two main ones. One way is just to try different x values until you can separate the a and the b. So let's break this up into different methods. We'll say method 1. With method 1, just try different x values. And usually you want to try the x values that would make some terms disappear. If I try x equals -2, that'll make this whole parentheses go to 0, which will leave the a by itself. So plugging -2 in, I'm going to get -12 plus 7. That's going to be equal to the a. Remember, this whole term was just 0. So this tells me that a has to be -5. Okay, now that I have the a, I can find the b. There's no other numbers that'll make stuff disappear, so I'm just going to plug in x to be 0, just because it's usually a nice thing to plug in. 6x times 0 is just going to be 0, so 7 on the left. Remember that this a here is now -5, plus, if I plug 0 into this, I'm just going to get 2b. Add the 5 over. Oops. Divide by 2. So I get b is 6. Okay, so that's one way of doing it. Let's look at method 2. Sometimes method 1 is easier, sometimes method 2 is easier. So just starting back over from the beginning here. For method 2, you cannot have any parentheses, so you have to multiply everything out. So we're going to leave the 6x plus 7 on the left-hand side. The a is fine, but I'm going to distribute that b into the parentheses. All right, now what you want to do is a pretty clever trick here, is you want to take all of the coefficients on the different power functions and set them equal. We have linear terms with just a single x, and we have constant terms. So let's look at all of the terms that have an x on it and set the coefficients equal. On the left-hand side of the equation, we have a 6x. On the right-hand side of the equation, we have a bx. That tells me that b has to be 6. We also have constant terms floating around. On the left-hand side, we have a 7. On the right-hand side, we have an a plus a 2b. But remember that the b is 6, so now it's 12. And when I subtract 12 over, I get -5. So we get the same two constants that we got with method 1. I don't care which method that you use the one that you think is easiest for the question. Like I said, sometimes ones are easier than the others. All right, so basically, just kind of going back up, remember that we were trying to find the partial fraction decomposition for this. What we're going to do is set this equal to the right-hand side where my a was -5 and my b was 6. So just kind of rewriting it, 6x plus 7 over x plus 2 all squared, we are going to say is equal to -5 over x plus 2 all squared plus 6 over x plus 2. All right, and then don't forget the whole point was that we were trying to do the integral of this. Right, so we were integrating over this complicated fraction. Instead, we're going to integrate over -5 over x plus 2 all squared dx plus the integral of 6 over x plus 2 dx. All right, now we want to do these separately. They're not too hard at this point. This first one, excuse me, I guess both of them really are going to be a u substitution, where we're going to let u be x plus 2. So then du is just dx. That makes this first integral, pulling the -5 out of the integral, to just be u to the -2 du. Plus this one, pulling the 6 out, will be the integral of just 1 over u. All right, u to the -2, we're going to raise that up to be a -1 and then divide by that negative. For this one over here, the antiderivative of 1 over u is the natural log of the absolute value. All right, last step's to plug back in the u. So this is going to be 5 over, moving that to the denominator, x plus 2 plus 6 natural log of the absolute value, x plus 2. Okay, great. So I hope you can kind of see how partial fractions can help us out here. All right, let's do one more example for this. So let's try this one. So the integral, -2x plus 4, all divided by x squared plus 1 times x minus 1 all squared. All right, again, right, we have all kinds of techniques so far with doing these integrals, but there's nothing that's going to help us out here except for partial fractions. Our denominator is always already factored as much as it can be factored, so let's break this thing down. We're going to set this equal to, so I have this quadratic, x squared plus 1, so that's going to get its own fraction. But because it's a quadratic denominator, it's going to have a linear numerator. The next thing we have is this x minus 1 all squared. So that's going to get its own fraction for x minus 1 squared with a constant up top plus just a fraction with x minus 1 with a constant up top. All right, now we have to find the a, the b, the c, and the d. All right, there's plenty of ways to do it. We're going to multiply everything by the denominator here. When I multiply it onto this first fraction, I'm going to get that numerator ax plus b. The x squareds plus 1 cancel, but I still have x minus 1 all squared. Multiplying onto this next fraction, I'm going to get that c. I'm going to get the x squared plus 1, but the x minus 1 all squared canceled out. Finally, the last one, I'm going to get the d. I'm going to get the x squared plus 1, and I'm going to get a single x minus 1. All right, again, kind of up to you how you want to find the a, the b, the c, and the d here. I think the best course of action would probably be to multiply all of this stuff out and then do that coefficient trick. So this is going to get kind of ugly here, so just bear with me. Make sure you take your time when multiplying all this stuff out. So first thing I'll do is I'll square that x minus 1. X minus 1 squared is x squared minus 2x plus 1. Go ahead and distribute the c into the parentheses here. I'll leave the d outside for this one and then just FOIL these two things together. All right. I'm probably not going to have enough room to write all this out, so I'll have to make 2 lines, but now we need to multiply these two things together. I'm going to multiply the ax times these 3 terms, and then the b times those 3 terms. Copying down the cx squared plus the c, and then distributing that d into all of this. So it looks like I will have enough room, which is nice. Okay, so we have cubed terms, squared terms, linear terms, and constants. We're going to get 4 different equations here. Let's look at the cubed terms first. On the left-hand side of the equation, I do not have any. On the right-hand side, I have an ax cubed, and I have a dx cubed. Since I've already used these 2, I'll go ahead and cancel those out. All right, for my x squared terms, I have 0 on the left. I have a negative 2a, a plus b, a plus c, and a minus d on the right. All right, I have my x terms. I have a negative 2 on the left, a negative 2b, and a plus d on the right. And then finally I have the constant terms. So 4 on the left. Looks like I have a b plus c minus d on the right. Okay, great. Now we have these 4 equations, and you just want to solve for the a, the b, the c, and the d. This is algebra stuff. There's many different ways to go about doing this. I know these look kind of awful looking, and they kind of are, but just a lot of substitution, a lot of elimination stuff if you want to do that. For some of you that know how to do it in the calculator, then by all means do this in the calculator. Whatever you need to do to get the a, the b, the c, and the d. This video is already getting kind of long, so I'm just going to go ahead and write out what the answers are. Looks like the a is 2, the b looks like it's 1, my c I think is also 1, and then the d is I think negative 2. Just double check in my head real quick to make sure I got these right. Yeah, they look right. Okay, cool. All right, so using these constants now, we're going to plug that back into the partial fraction decomposition that we have from up here. So we have ax plus b over the x squared plus 1, c over x minus 1 all squared, and then d over x minus 1. That means that that thing from up top, way up there, is going to simplify down to be 2x plus 1 over x squared plus 1 plus negative 2, oh, sorry, nope, wrong one, plus 1 over x minus 1 all squared, and then plus negative 2 over just x minus 1. All right, and then don't forget that we want to integrate over this whole thing. So we're splitting this up into 3 different integrals. let's look at each of them. So let's look at the integral of 2x plus 1 over x squared plus 1. We'll do this one first. We also have the integral 1 over x minus 1 all squared. That one shouldn't be too bad. Plus we also have the integral negative 2 over x minus 1. That'll probably be the easiest. All right, let's look at the more complicated one. This one out in front. So again, this is going back to section 1 techniques. What we're going to do here is we're actually going to split this up into two separate fractions. We're going to have the integral of 2x over x squared plus 1. That'll be a nice u substitution. Plus the integral of just 1 over x squared plus 1. All right, and then we have these over here still. Okay, so each one of these separately. The first one here, like I said, it's a u substitution, where we let u be the x squared plus 1, and the du would be the 2x dx. That'll cancel out with the 2x dx that's already up there. This will just be the integral of 1 over u du, which is going to be a natural log. This one, we're going to get from the integration table. I don't remember exactly which number it is. It's either number 18 or 19. But this is going to have an antiderivative that is the tangent inverse. Okay. This one is going to be technically a u substitution, but I've already used a u, so let's use v. V is x minus 1, and then dv would just be dx. So this would be the integral of 1 over v squared dv. This would also be a u substitution, but I hope at this point you guys can kind of see what this is going to be. For this one, it's going to be a natural log problem. So we're going to bring that negative 2 out, and then this is going to be the denominator is the inside of the natural log. Okay, going back to the beginning. For this first one, the antiderivative of 1 over u is just natural log of the absolute value of u, but don't forget the u for this one was x squared plus 1. All right, that plus, remember this one we said was from the table. That's that tangent inverse of x. This one is going to have antiderivative of negative 1 over v. Remember, v was x minus 1, so it's going to be negative 1 over x minus 1. And then minus 2 times the natural log of the absolute value of x minus 1 plus c. Okay, great. So I know it's long, I know it's awful looking, but that really is the antiderivative of what we started with. Sometimes on the homeworks they may combine the natural logs together, so just keep that in mind. So if you see where you think you should have two natural logs, there's only one. That's because they're using natural log rules to combine them together. I know these are hard, and I know these take a lot of time, so as always, ask questions for homeworks.